All right, we looked at a Taylor polynomial, P0, P1, P2, and P3 for natural log x expanded about x equal 1. So now we'll look at a special case where we take functions and we expand about x equals 0. Those special cases are called the Maclaurin polynomials instead of Taylor polynomials. Remember, it's the same process. On Maclaurin polynomials, you're simply doing an expansion about x equals 0. Okay, so in these examples here, I got one that's e to the x, the other one it's sine x, the other one's cosine x. They want us to find P0, P1, P2, P3, where we expand about x equals 0, and so that's a special case called the Maclaurin polynomials. So for all of these, we're going to need the first derivative, the second, and third derivatives. Okay, so if we look at the first one, f of x, e to the x, the really nice thing about that one, all the derivatives, so the first, second, third, fourth, f superscript n derivative is going to be e to the x. And e to the x evaluated at 0 is going to be 1. Remember, we would take f to the nth derivative evaluated at a, but a is 0. So in all of these, the coefficient c sub n is going to be the nth derivative evaluated at 0, which is just 1, divided by n factorial. So C0 will be 1 over 0 factorial. C1 will be 1 over 1 factorial. C2 will be 1 over 2 factorial, etc. So let's look at that one for the first one. Okay. So here's f of x, e to the x, and all of the derivatives. Doesn't matter f prime, f double prime, f, the nth derivative of f is all e to the x. So f at 0, f prime at 0, f double prime at 0, they're all 1. Okay. So P0 is f at 0, which is 1. P1 is f at 0 plus f prime at 0 times x. All right, remember, this is x minus a, but a is 0. Okay. So this is going to be 1 times x, so there's the x, and then I have the 1 from the previous step. P3 is f sub 0 plus f prime at 0 at x plus f double prime at 0 over 2 factorial x squared. Remember, the degree of x minus a, in this case just x, goes up every single time you take another derivative. All right, so this is going to be 1 over 2 factorial, which is 1/2. So we have 1 plus 1/2 x squared. If I take P3, I'm just going to add a 1 over 3 factorial, which is 1/6 x cubed. Right, here's the 1 over 3 factorial x cubed, which of course is 1/6. And in general, for e to the x, it's 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot, 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 x to the n over n factorial for the nth Maclaurin polynomial. And here they've got it packaged here in concise terms. P sub n is k equals 0 to n over x to the k factorial. So here they've packaged it into a nice, neat formula for the Maclaurin series for e to the x. Okay. Let's think about sine x. Okay. So if I do this one here, now we're going to be evaluating all of these at 0. So the first coefficient, c sub 0, is going to be sine of 0, which is 0. But f prime is cosine x, and cosine x evaluated at 0 is 1. So I'm going to get a 1 over 1 factorial. Times x would be the term corresponding to f prime of x. F double prime of x is going to be minus sine of x. And minus sine of x evaluated at 0 is still 0. So all the odd powered, all the odd derivatives will be 0 because I'm going to get a version of sine in there. Let's go ahead and see the details there. Oh, by the way, here they're plotting each of these polynomials for e to the x. Here's p sub 0, it's a constant estimation of e to the x. Here's p1, it's a linear estimation of e to the x. Here's p2, which is a quadratic estimation of e to the x. And p3 is a cubic estimation of p to the x, all evaluated at or near 0. Okay. All right, so getting back to the second example. F of x is sine x, f prime is cosine x, f double prime is minus sine x, f triple prime is minus cosine x. The fourth derivative is sine x. Okay. And so I guess I misspoke there. All the even derivatives here are going to be 0. Right? The second derivative is sine x with a minus sign, and I evaluate that at 0, I get 0. The fourth derivative of sine of x is, the fourth derivative is sine of x again, and so I get, evaluating that at 0, I get 0. Okay. You can think of this one here, f of x is the 0th derivative, meaning don't take a derivative, and I get 0. So all the even derivatives are going to have zeros. Okay. So when I put this together, here they say that f, here I have 2m derivatives, so when m is 0, 1, 2, 3, all the even derivatives are 0 when I evaluate them at 0. Right? Evaluate at 0, I get 0. Why? Because the even derivatives are going to be some form of sine, and when I plug in 0, I get 0. All the odd derivatives will be minus 1 to the m power. If you look at that, there's the first derivative, that's a positive 1. The third derivative, I get a minus 1. The fifth derivative, I'll get a plus 1. So that's where they come up with this formula here. Okay. So P0 is 0. P1 is 0 plus x. Right. Here's the f prime at 0 at 1 is 1x. P2, I have a 0, then there's the x, then I have a 0 term here. So I just get x. P3 is 0x, 0, and here I have x cubed, and I'm going to have a minus. Remember, it switches sign. So all the odd ones switch sign. There's positive, then negative. P5 is going to be a positive again. Okay. And all the even terms are just going to contribute zeros. So 0, 0. Sorry, even derivatives are going to give 0. It turns out to be the odd terms are 0. Okay. So it's only going to collect the odd powers of x. X cubed, x to the fifth. And you can think of this as x over 1 factorial minus x cubed over 3 factorial plus x to the fifth over 5 factorial. If I did P7, I'd have minus x to the 7 over 7 factorial. Okay. So they're going to package this nicely. I only need to collect the odd powers of x. Okay. And so here, the P2m plus 1, that guarantees I have an odd polynomial here. Right. The Maclaurin polynomial defined by 2 sub 2m plus 1. It's going to be x minus 2 minus x cubed over 3 factorial plus x to the fifth over 5 factorial. And you go out to minus 1 to the m, x to the 2m plus 1. That, notice that'll be an odd exponent on m, over 2m plus 1 factorial. Okay. So if if m were, let's say it were 5, right? Then I'm going to have 5, I'm going to have 1, 2, 3. So if I put a 0 in here, I'm going to get a 1. If I put a 1 in here, I'm going to get a 3. If I put a 2 in there, I'm going to get a 5. So it'll only be the odd powers, and it'll switch sign. So this is a nice, neat packaged formula for the Maclaurin polynomials. Here's what it looks like as a graph. Okay. This dark blue is sine of x, and here I've got a linear estimation, that's P1. Here's a cubic estimation, that's P3. Here's a fifth power polynomial, that's P5. Okay. All right. So lastly, let's look at find a Maclaurin polynomial for cosine. So if sine of x is a template, then notice that cosine x, every single time I take two derivatives, I get to cosine and some version of cosine. And cosine of 0 is going to give me a 1. So the even derivatives will give me 1s and minus 1. And the odd derivatives, right, will give me zeros. So it's going to be kind of similar. Let's see what gets collected here. Okay, so we're going back to cosine. So There's cosine, evaluated at 0, I have 1. The first derivative, there's minus sine, I get a 0 when I evaluate it at 0. The second derivative is minus cosine x, evaluate at 0, I get minus 1. The third derivative, I get sine x, evaluate at 0, it's 0. Okay. So notice all the odd derivatives give me zeros. Okay. And before, when I had f of x equals sine x, all the even ones gave me 0. Okay. So that means only the odd ones are contributing. The even ones are contributing. Right. Fourth derivative, second derivative, and I'm going to change sign. So f2m of 0 is minus 1 to the m power. So notice this is an even derivative here, evaluated at 0. It's going to be plus or minus 1, depending on m. Okay. And the odd derivatives, that's superscript 2m plus 1, are all 0. Okay. So p0 is 1, p1, this is the c0, this is c1. Now it's odd, so it's going to be a 0. p2 is 1. There's this c1, which is 0. And there's the c2 is going to be 1 over 2 factorial with a minus. There's x squared. Okay, so I'm only getting here the even powers of x. X squared, x to the 4th. You can think of this as 1 times x to the 0 power. So I'm really only getting the even powers of x. And it's alternating sign. So the cosines, if I package this nicely, k equals 0 to m, minus 1 to the k. Here I'm getting only even powers on x. And so the cosine expansion for the Maclaurin expansion gives me all even powers. And the sine expansion, when I do the Maclaurin expansion, gives me only the odd powers of x. And if we really look at, the graph of cosine and sine. So, by the way, here's P0 estimation for cosine. Here's the cosine in dark blue. Here's P2, it's quadratic. Here's P4, it's quartic. So we're using even polynomial to estimate an even function, right? Cosine x is an even function. We look at, here's the sine version here. Sine of x is an odd function, and it doesn't surprise us that the polynomials are all odd functions, P1, P5. So it's kind of interesting, it's beautiful, but it shouldn't be too surprising. Sine x is an odd function around the origin, and so we're going to have these odd polynomials, P1, P5, P3, as a best estimate, because those are all odd functions. Similarly with the cosine function, right? Cosine function is an even function, and here we've got all the even Maclaurin polynomials, P0, P2, P4. Okay. So whenever you're doing these, you ultimately have to do a couple things. You've got to take derivatives, okay, evaluate them at, in this case, x equals 0, okay, and then if you can, repackage them in a nice, neat formula.